I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the AP Physics 1 2025 FRQs. This is question 3, the experimental design question. In this video, we're going to continue our 2025 AP Physics 1 FRQs. This is question 3, the experimental design question. So in this question, we're given students are investigating a balancing system using the following setup where you've got a meter stick that's balanced on a stand. You've got a spring scale at one end at 0 centimeters, and then you have holes where you can hang an unknown mass at 60, 70, 80, or 90 centimeters. And the hook is what we're trying to find the value of the mass by hooking the mass in different places. So what we're going to do is, since it cannot be attached to the spring scale, we're going to collect some data. So the students are asked to take measurements that will allow the students to create a linear graph whose slope could be used to help find the value of the unknown mass of the block. So we're going to describe an experimental procedure to collect data that would allow the students to determine M naught. So we have to include any necessary steps to reduce experimental uncertainty. So the first thing we're going to do is we're going to hook the block on the meter stick at 90 centimeter. Then we're going to pull down on the spring scale until the meter stick is balanced horizontally. We're going to record the measurement that we have on the spring scale. And then we're going to move the block to each of the remaining positions and repeat steps 1 through 3. Then we're going to use 10, 20, 30, and 40 centimeters in place of 60, 70, 80, and 90 because that's the position away from the center of the meter stick. So we're going to record those values and change our positions from 60 to 90 to 10, 20, 30, and 40. Then the point that's always important is the uncertainty. So maybe when we pulled the spring scale down, it wasn't completely horizontal. So we're going to repeat the process for each of the 4 positionings of the block. And we're going to do that at least 10 times to reduce uncertainty to make sure that the meter stick is completely level. Then we're going to describe how we're going to use the procedure that we said in part A and the data we collected to create a graph that would be able to find the slope value and find the mass of the block. So the first thing we're going to do is we're going to use a balanced torque equation for the meter stick. So we're going to write counterclockwise torques equal clockwise torques. Now the counterclockwise torques, if we look, we can pull down on the spring scale. If we pull down on the spring scale, that's going to cause a counterclockwise rotation. And if we just let the mass hang on the other side, it's going to cause a clockwise rotation. So what we're going to do is we're going to take those forces and turn them into torques by multiplying by their distances. So the spring scale force times 0.5 meters is going to equal m naught g, which is the force of gravity on the block, times r, which is the distance it is from the center. That's the 10, 20, 30, 40, 50 centimeters, or 0.1, 0.2, etc. Then what we're going to do is we're going to plot 1/2 of fs on the vertical axis, and then we're going to plot g times r on the horizontal axis. And when we do this, if we look, fs times 0.5 meters equals m naught g times r. That's in the form of y equals m times x, where m is our slope, and that also represents m naught. So once we find the slope of the graph, that's the slope represents the mass of the block, and that's how we can find the mass of the block using the setup that's given to us. Now the students have an identical meter stick, a mass m, that is now attached to an axle that is fixed to a wall. The meter stick is free to rotate with negligible friction about the axle. The meter stick is suspended horizontally by a string that is connected to a spring scale of negligible mass as shown in figure 2. And the angle theta that the string makes with the meter stick can be varied by attaching the string to different pegs along the wall. And the students use the spring scale to measure the tension force required to hold the meter stick horizontal, and table 1 shows the values of theta and ft. And the students correctly determine the relationship between ft and theta is given by ft is equal to 5 mg divided by 6 sine theta. The students then are going to create a graph with 1 over sine theta plotted on the horizontal axis, and we're asked to indicate what value can be measured on the vertical axis so that we can experimentally find the value of the mass of the meter stick. So I'm going to show you two different ways to do this. So the first way that we're going to do is we're just going to graph the tension force on the vertical axis. So if we graph the tension force, we don't have to do anything with that column, but so our task is now on the blank graph provided. We're going to graph the quantities we stated in part C1 to determine the mass of the meter stick. So first, we have to use table 2 to record any points or calculated quantities that we need to plot. Well, we know we have to do 1 over sine theta, so we have to make sure our calculator is in degree mode. So we'll take 1 divided by sine of each of those angles, and we get these values from our calculations. So now we're ready to do the next step. We need to clearly label the vertical axis, including units as appropriate. So the vertical axis, we're just going to label with tension force in newtons, and it goes up to a maximum of 21. So we've got 5 lines. So we're just going to label them by fives from 5 to 25. Now our next task is to plot the points we recorded in table 2. So 1 over sine theta is our x value, and ft being our vertical value. So we're going to plot 2.7 and 21, 1.9 and 17, 1.7, 13, 1.4, 12, and then 1.0 and 8. So now we've created our graph. The next step is we're going to draw our line of best fit. So here's where, again, you need that ruler so you can make sure that you draw a straight line, and you can have a nice perfect straight line, so we hopefully can use that to find our next step, which is to determine the slope of the best fit line to calculate the value of the mass of the meter stick. So what we're going to do is we're going to pick 2 points to find the slope. So I'm going to pick the point at the end, which is 325. So we can use that 25 over 3.0. Then we can pick another point, which I'm going to pick here, which is 8 on the vertical axis and 1 on the horizontal, so 1, 8. And remember, 1 over sine theta does not have a unit, but tension force does, so we're going to use newtons in the numerator. So newtons is not a measurement of mass. We know that this slope does not give us the answer that we're looking for, but we get 8.5 newtons. Now, how are we going to determine the mass of the meter stick? Well, let's look at the equation that the students derived, and we have Ft equaling some value times 1 over sine theta. So that's y equals m, which is the slope. Anything that's not sine theta is going to be our slope. So that 5 mg over 6, that's going to be the value of our slope. So we're going to substitute, rearrange this equation and solve for m. So we get 6 times the slope divided by 5g. Now we can plug values in. 6 times 8.5 newtons divided by 5 times 9.8 meters per second squared. Well, newtons over meters per second squared, that's force divided by acceleration. Force over acceleration gives us a mass. So that tells us that the mass value is going to be 1.04 kilograms when we find the value of the mass using this graph. Now, what if we do it a different way? So let's look at a different method that we can do. So bringing back all of the information that was given to us. Now, if we rearrange this equation that's given to us, and we solve for m divided by sine theta. So we get 6ft divided by 5g, and that equals m divided by sine theta. So y would be 6ft divided by 5g. That equals m, which is our slope and also the mass, and 1 over sine theta is the horizontal, so we can graph 6ft divided by 5g on the vertical axis. So now, looking at the same thing, we're going to record in table 2. So now we have some extra data that we need to record. So we calculate 1 over sine theta already, and now we'll do 6 times the tension force divided by 5g, and that's going to give us tension divided by an acceleration is going to give us a unit for mass in kilograms. So now we're going to clearly label the vertical axis again. So we're going to graph 6ft divided by 5g measured in kilograms, and those values go up to 2.6. We're just going to label those 1 through 5. That still lets us use more than half of the graph to get that point on the scoring rubric. Then we're going to plot our points we're going to plot 2.7, 2.6, 1.9, 2.1, 1.7, etc., all the way to 1, 1 for our last data point. Then we're going to draw our line of best fit. Then after that, we're going to use that line of best fit to calculate the experimental value for the mass of the meter stick. Well, graphing it this way makes it easy because the slope is the mass. So all we have to do is pick 2 points to find, and we have 3.2 in the vertical and 3 in the horizontal. And I'm going to pick 1, 1 as well. And then we know that the unit for 1 over sine theta, there is no unit, but the unit on the numerator is kilograms. So when we solve that, we get a mass of 1.1 kilograms. When you're finding slope, you can do it one of two ways. The way I showed you is just picking 2 points that are on the line, not data points, but points that are on the line. Or you can type the data into your calculator and use the linear regression, but you have to state that you used your calculator to find the linear regression. You can't just have a magical number appear and not explain where that number came from. So make sure if you use your calculator, you explain where the numbers came from. So this is the 2025 AP Physics 1 FRQs. This is question 3. I hope this was helpful. I hope you have a great day and even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.